We're going to go ahead and review some log and exponential stuff, and then we'll be getting into taking the derivatives of exponential functions and doing some integration. So remember, an exponential function is a function where your variable x, or whatever variable you happen to be dealing with, is in the exponent. So it's a number raised to a power of x. And then you should remember that the inverse of an exponential function is referred to as a logarithmic function. And here I just highlighted the um, logarithmic form of that, and over here I just highlighted the exponential form. You can go from one form to the other form using this definition of a logarithm. Please make note that anything after your logarithm always has to be positive, and that's what this is saying right here. So down below we have our exponential rules that most of you should be very familiar with. The last one maybe not as much, but if you have a to a power equaling a to another power, if the bases are the same, then the exponents have to be equal. It's really what it's saying. And then to review logs, if you have the log of two things multiplied, you can break it apart, go log of the first times, or plus log of the second. And that's all related to this exponential rule over here. Same idea with the log of two things being divided, you go log of the first minus log of the second. Or if you have an exponent after your log, you can put the exponent down in front. And so we also have, just as a reminder, if there is no base written after your log, it's assumed to be log base 10. Or if there is a natural log, remember that that is log base e. So to just review, solving an exponential function like this, you want to get the part with the exponent on one side by itself. In this case, it is. If you are adding or subtracting something to your e, then you'd want to get that by itself. Once you have it by itself, e to a power by itself, you could do a couple of things. One of the things is basically take the natural log of both sides. Remember, natural log of an e, they undo each other, and we would get this. Another thing you could do is you could go from the exponential form right here and use your definition of a logarithm, and if you did that, then you get straight down here. Either way, you still get down there, and then you got to finish getting x by itself, so you go ahead and subtract 1 from both sides. This is your exact answer, which is also your calculator-ready form. You could type it into your calculator if you wanted to and get this. So on this problem, to solve it, you need to get the log by itself, which it is, and there's two ways to go about it. You could go ahead and exponentiate both sides. Basically, you take and go e to each one of these and kick each one of these up as exponents. Or you could remember that this is log base e of this, and then just use your definition of a logarithm, which remember basically takes this, swings it over, hits the 5 up as the exponent. But whether you exponentiate both sides, you use definition of a logarithm. In other words, you end up getting this. Because remember, your e undoes your natural log. Then you got to finish getting x by itself, so you'd have to go ahead and add 3 and then divide by 2 or multiply by a half. And this would be your calculator-ready form, and then you could go ahead and type it into your calculator. So just as a review for your natural exponential function, remember your natural exponential function is just y is equal to e to the x. For the most part, whether it's a natural exponential function or a normal exponential function, your domain is all real numbers, your range is always greater than 0, it's continuous, it's always increasing if your base right here is greater than 1, which e is, because remember e is about 2.7. And it's always going to be concave up, assuming that your base is greater than 1. Now, this is what you see over here, the graph of e to the power. Well, let's have your calculator do the derivative of e to that power and graph that too. So in your y equals, go ahead and put in your normal e to the x. Now, depending upon the version of your calculator, go down to y2, then hit math, go down to end deriv. It'll either pop this up or something like this. So what you'll want to do is you'll want to go ahead and put in y1 here or y1 here. Remember, to get to y1, you go vars, arrow to the right to y vars, and then select 1. And then you're also going to have to put in x comma x in this form, or you'll just have to put in your x right here in this form. And then hit graph. And you'll notice your derivative really ends up going over the top of your original function. So in other words, does your derivative of e to the x compare to e to the x? Well, they're the exact same thing. So in other words, if you have y is equal to e to the x, well, the derivative is also e to the x. It's very uncommon where your derivative is equal to your original function, but in this case it is. However, just remember that if it's not just an e to a normal x, it's e to, say, a different function, then you basically have to do the chain rule. So the derivative of e to a power is e to that power times the chain rule, which would be the derivative of the exponent. So looking at this, we have e to a power, so when we do our derivative, it's going to be e to that power, then chain rule times the derivative of the exponent, which you know is 4. It's common practice then to put this normal 4 right in front of your e, and then that would be your derivative. Same idea over here. When you do e to a power, well, it's still going to be e to that power, but then chain rule times the derivative of the exponent, which you know is -2. So then it's common practice, just put that -2 in front. Here we have y is equal to e to the k times x, where k is a constant, just like what we had over here on the left. So it's really going to be e to that power times the derivative of the exponent, which is just that constant. So it's common to just put that constant in front. Well, looking at this problem, to do our derivative, well, you can see that we have variables times variables, so you'd have to use the product rule. So you'd do the derivative of the first, gives you 2x, times the second, plus the first times the derivative of the second, which would be e to that power, times the chain rule derivative of the exponent, which would just be -1. So in other words, we could simplify this last little part by basically writing it like this. Now, you could leave it like this, but you could also go ahead and pull out your common factor, and you would get this. A lot of times you're going to want this because you're going to have to be looking for your zeros of your derivative, because remember, a lot of times we're looking for max and mins and increasing and decreasing, and that's when your derivative is equal to 0. So it's typically easier to have it in the factored form. And then in this case, if we needed to, you'd have 3 things multiplied together to give you 0. So you could set each one equal to 0. Over here, we're dividing variables, so you'd have to do the quotient rule. So you do derivative of the top, which is e to the power, chain rule times derivative of the exponent, which is a 2, times the bottom, minus the top, times the derivative of the bottom, derivative of the bottom is just a 2, all over the bottom squared. So at this point, if you wanted, you could go ahead and pull out some common factor stuff, what's the same before and afterwards, and well, you could pull out a 2 to a power. And if you wanted, you could also pull out this timesing by 2. You could either do that, or since it's not that difficult basically to distribute through, you could do it that way too. If you would distribute the blue into the red, and blue and red give you purple, you get this here. Then you can see these last 2 terms cancel each other out, leaving you just the first thing over the bottom. you would still get the same thing even if you had pulled out your common factors up there. You still would have eventually got down to this. So on this problem over here, we talked about doing our derivative, and then we said a lot of times you want it in the factored form because you want to find your max and mins. Well, this is that exact same problem to where you're looking for max or min, so we'll take our derivative from the previous slide. Well, then once again, you would have three things multiplied together to give you 0, so you can set each one of these things equal to 0, so that x could be 0, that e to the x could be 0, or the parentheses could be 0. Well, if you set the parentheses equal to 0, solve it for x, you get x to be 2. Remember, e to any power is always positive, so it's never going to be 0. Or this one here. So we get our two critical points of 0 and of 2. And to find max and mins, remember you have to put them on a number line and a labeled number line. So we put on 0, we put on 2. Now we can try a number to the left of 0, like -1. It's labeled as first derivative, so we plug it into our first derivative. And we plug it in. This would be a negative. E to any power, remember, is positive. 2 minus a -1 is positive. So when you take a positive times a negative, you know that you end up getting a negative. So you know to the left of 0, you're decreasing and going down. You could try a number in between 1, like 1, which is in between your 0 and 2. And if you do that, we could try that, like 1. 1 here is positive. 1, e to this is positive because e to any power is positive. 2 minus 1 is positive. If everything is positive, you know you multiply and you get a positive. So you know you then have to be going up. So therefore, this is a minimum. Taking a look over here on the right, we could try like 3. If we tried 3, we'll go ahead and get rid of this over here and try 3. 3 in for x is positive, and we're not writing. E to the power is positive, then you'd have 2 minus 3, which is negative. So positive times a negative is a negative. And so you would know you'd be going down, which is top of a mountain, so you know that that's a maximum. You're actually looking for the local max and min, so that means you've got to actually plug these into your original function. Take 0, plug it into your original function. Well, 0 times e to the 0 would be 0, so that's your minimum. Plug in 2, you get 4 times e to the -2. And so that would be your maximum. Now, for those of you that have had stats, you should know that what we have here is your formula for being able to do your normal density curve. If you did your derivative of this, remember, it's just a number times e to a power. It's going to be that number times e to that power, and then you just have to do the chain rule, derivative of the exponent, and that's why we get this -x. If you are looking for inflection points, remember you have to do your second derivative. Well, you'd have variables times variables, so you'd have to do product rule. Well, if you work your product rule all the way out, you just get this right here. And remember, your critical points are where your derivative is 0, so you'd set this equal to 0 and you could solve it. Well, this is just a number in front, never going to be 0. This is e to a power, never going to be 0. So then all you really have to do is just set this equal to 0, and you end up getting x to be plus or minus 1. In other words, that 1 standard deviation is where your points of inflection are on either side. It's where it switches from concave up to concave down, and then back to concave up. That's just a quick side note of how calc does relate to stats. So we know the derivative of e to a power is e to that power, so therefore the integral of e to a power is e to that power. So let's look at this problem here. We have Variables times variables. Well, for one thing, we know we could go ahead and pull that 5 out in front of your integral sign. Well, a lot of times when you have variables times variables, you want to use a u substitution. Not always, but a lot of times. So you could either let u be x or u be the negative x squared. Not always, but typically you want u to be the higher power. Well, if we do our du, we end up getting a negative 2x. Well, we have that. We don't have an extra 2, negative 2 hanging out inside our parentheses. We just want to end up with an x dx. So to get rid of that negative 2, you'd actually have to multiply both sides by negative 1/2 or divide by negative 2. So we're going to leave that 5 in front. We're going to replace our red negative x squared with just u, because that's what we set up here. We're going to replace the blue of x dx with that negative 1/2 du. Well, we're timesing by negative 1/2. We could just pull that negative 1/2 in front with our 5. And then we just have the integral of e to a power. Well, integral of e to a power is just e to that power. And then we could substitute in what u is, which once again, u is that negative x squared. And so that's our integral. Now, also remember, being an indefinite integral, you have to go plus c. Looking over here, we're dividing by variables, so a lot of times you have to use a u. Remember, you typically want u to be the higher power, which could be either 1 over x, or remember, this is an x to the negative 2 here. So you typically want u to be the higher power. Well, here you have x to the negative 1. Here you have x to the negative 2. So you let u be the higher power. You do your derivative, which is really what we have showing up in our problem. So we have e to the u. Instead of doing the blue, it's just this negative du. Oh, well, that negative we could pull in front. And now we're just integrating e to the u, which is pretty easy. We know we're going to have that negative. E to the u is e to the u with a plus c, because we integrated. And then you plug in what u was, which was just 1 over x. Over here, we have the integral of sine e to the cosine of x, which once again, we're multiplying variables. So a lot of times you want to use a u. We're going to let u be what's in our exponent. Because if we do that, then we get a sign to show up. Happens to be a negative sign. We don't have a negative in our problem. So we're going to go a negative du is equal to our sine of x. So when we look at this, we're going to put our negative, or our sine of x with our dx. So that blue gets replaced with negative du. And then instead of doing the red, that's our u. And then we just have the integral of e to the u times the negative du. So you can pull that negative in front because you're timesing by negative 1. Well, the integral of e to the u, you know, is e to the u with a plus c, because it's an indefinite integral. And then just plug in what u is, which is cosine of x. Now we just have one problem left. Happens to be a definite integral because we have bounds right here. Well, u is going to work good here because we're dividing by variables. U does not always work, but a lot of times if you're doing variables times variables or variables divided by variables, a lot of times it works, but not always. We're going to let u be the bottom. Well, if you do your derivative of both sides, you get du to be just x dx. Well, that works out good because your x dx is really what we had there. Because remember, this e to the x is really putting it afterwards, and timesing by it is really the same as putting it on top, because if you put this over 1, it puts it on top. So we really just have our du here, and then we 1 over u here. But being a definite integral, we have to change our bounds, because our bounds here are x's. So we have to change our bounds down here to be u's. Oh, well, if x is 1, to figure out your u, all you'd have to do is take 1 and plug it in here for x. And well, you just get 1 plus e. So when x is 1, your new u bound is 1 plus e. Similarly, we got to take 0 and plug it in up here for x, and we get 1 plus e to the 0, which would be 1 plus 1, which is 2. So instead of writing 0 as my lower bound, when I rewrite it with u's, my lower bound is 2. Well, now I'm just integrating 1 over u. You should remember when you integrate 1 over u that that's just natural log. Then you have to evaluate it from your upper bound to your lower bound. So plug in your upper bound, natural log of 1 plus e, minus what you get when you plug in your lower bound, natural log of 2. And if you wanted, you can remember that a log minus a log, you could just divide what's afterwards.